Pleased to welcome Zach Slepian from Florida to give our first presentation on high energy physics at the high number density frontier. So I'll give you the usual warnings for the event.
Thanks. Okay, thanks, Chris. Thanks everyone for being here. I am very happy to have made it here after a lengthy sequence of flights. And so you may wonder why I have this picture. Well, this is a famous drawing by M.C. Escher. And as you can see, it has some hands drawing each other. So I chose this for a reason, and you'll see that reason shortly. But now I just want you to kind of keep it in mind to stimulate your thinking. And so today I'll be talking about, okay. There we go. Today I'll be talking, as Chris said, about high energy physics at the high number density frontier, in particular probing parity violation with the galaxy 4-point function. And this is work done with my former postdoc, Jiamin Hu, who is now at MPA in Germany after just finishing a couple-year postdoc with me in Florida. And then also this is work with my Berkeley colleague, Bob Kahn, who in retirement got into cosmology after a long and distinguished career in particle physics. So in this talk, there will be some particle physics connections as well. And I'll try to highlight Jiamin's many contributions. But I should also say I'm very happy to be part of a Roman project infrastructure team with Yoon Wang and many collaborators, some of whom are in the room. And we're actually going to be providing infrastructure to the community to do 3- and 4-point correlation function measurements on Roman. So if you like what I say in the talk, 2 years from now, or maybe less, you can download our code and do this work yourself on Roman. So I hope that the talk will seed the kind of appetite for that. Although I should say what I'm going to talk about in the talk is non-standard, beyond standard model exciting science. So it goes beyond what the project infrastructure team is committed to do. So cosmology comes from the Greek cosmos and logos. Cosmos is everything, logos is logic or word. And it goes beyond word. It really means what is the kind of organization of everything. But of course, if you're going to ask what are the rules of the game, you need game pieces, you need matter, you need baryons, you need leptons, you need all of the standard model particles. So I think the most fundamental question in cosmology is why is there something rather than nothing? And of course, in the Bible, we have God shining light on the water. And in the Greek Testament, indeed, it starts with the word logos. God gave the word, there was light upon the water, and then he brought matter into existence. But this is a science conference, so I'd like to ask this question in a slightly different way, which is why isn't our universe filled with equal amounts of matter and antimatter? Because in fact, the standard model argues that this should happen. There are symmetries in the standard model where you basically get equal amounts of matter and antimatter. And of course, this would cause a little problem if it were true, because equal amounts of antimatter and matter would annihilate with each other. And then we'd have a very empty universe, although it wouldn't be completely empty. It would actually be filled with photons, and CMB observations would be really, really easy because the signal to noise would be incredible, but there would be no one there to do the observing. So why does our universe have something rather than nothing, more matter than antimatter? And in fact, this led to a need for CP violation. So CP is charge parity. Charge is positive and negative, but you can also think of it as matter antimatter that carries a charge. And parity is handedness. In detail, parity is actually just flipping your xyz to minus xyz. So it's a spatial inversion of the coordinates, and we'll come back to that. So CP violation means you're breaking the symmetry under flipping the sign of the charge and flipping the handedness. And in fact, in the 1960s, Sakharov, the Russian physicist, realized that having more matter than antimatter required breaking of this symmetry. And we don't need much of it. We only need 1 extra baryon for every 1 billion antibaryons. So you only need a 1 part in a billion breaking of this symmetry. It's explained by a hypothesized mechanism called baryogenesis, which is really a name for our ignorance. We don't know what did this. And in fact, the leading theory of what did this got ruled out a couple of years ago because the Higgs mass wasn't right and the Higgs boson mass tied to this theory. So baryogenesis, why there's more baryons than antibaryons to the tune of 1 part in a billion, is a major open problem in cosmology. And as I said, Sakharov pointed out that to do it, you need to break this CP symmetry. No physics that we know gives nearly enough. The only sector we have CP violation in is the weak force neutrinos. We only have left-handed neutrinos. We don't have right-handed neutrinos. And they're just not a strong enough interaction to give us the creation of more matter than antimatter. And so in this talk, I want to focus us on just P violation, just parity violation. Forget about the C for now. And let's just ask, what if it's P violation that's giving you the CP violation needed to explain the existence of more matter than antimatter? So as I said, parity is very simple. It's just a flip of x, y, z to minus x, y, and z. And you can think of it as a mirroring and a rotation. And in this talk, you can ignore the rotation part of this, because in cosmology, we average over rotations because we think that the laws of physics look the same in every direction. This is the assumption of isotropy. So for today, just think of parity, replace that in your head with the simpler word mirroring. It's just mirroring about a plane. And I want to show you how we can actually search for parity violation in the early universe. Now, we know that if it's playing a role in baryogenesis, it had to happen in the early universe because we've had baryons since the early universe, right? We know that at least during the first 3 minutes, we already had baryons because that's how you do big bang nucleosynthesis. So we know that if P violation will help us with this matter-antimatter problem, it had to happen early. We also know, as I said, that the only standard model sector that does it is the weak force, and it's very weak, so it's not going to be enough to do baryogenesis. So in fact, another way to interpret that statement is we know high energy physics well enough from Earth that we have to go back to a very early time in the universe when the energy scales are much higher than what we can probe at the LHC to have any changes to the standard model be allowed. So that's what I meant with the title being high energy physics at the high number density frontier. Inflation, of course, is when the universe is smaller and denser by orders of magnitude 10 to the 60 or more, in fact. And so inflation is a very high energy physics laboratory that we can never access on Earth. So how can we search for P violation in the early universe? Well, I'm giving you a hint with the background here. This background is actually a sample of 800,000 luminous red galaxies from Sloan Digital Sky Survey BOSS, and they're color-coded by redshift. So the yellow ones are closer, the redder ones are farther away. And this is a data set that we'll be talking about in this talk. So to search for parity in this data set, let's start with us. Let's start with our hand, because after all, I said, one example of parity violation in the standard model is we have left-handed neutrinos, but not right-handed neutrinos. So you might get a hint that there's a handedness when we talk about parity. And in fact, another way to see that is XYZ coordinate system. X cross Y is plus Z. This is a right-hand rule. If most of us were left-handed, we would have probably designed our coordinate system with a left-hand rule and said X cross Y equals minus Z. So you can think of parity as also a kind of handedness, so we can use our very own hands to investigate this. This, I thought, was also an appropriate image because this is actually a sketch by Michelangelo for the ceiling of the Sistine Chapel. And this is, of course, the famous image of God breathing life into Adam, creating, the human soul with his hand. So I'm not talking about anything so metaphysical today. I'm just talking about the, production of matter over antimatter. But I thought this kind of overtones of imbuing, matter with the soul was good because, of course, without more baryons than antibaryons, we wouldn't have us. Okay, so I just want you to do a very simple thing. Imagine tracing your hand. And this image is actually a still from a YouTube video showing you how to trace your hand. So if anyone is having a tough time with that, you can watch the video. But hopefully we all got this skill down somewhere along our way to the PhD. So imagine tracing your hand. Then I want you to cut out your hand, and you're going to imagine you traced it on black construction paper. So this is the cutout of your hand, and this white is just a background that, is just so you can see it. So imagine tracing your left hand, you'd get something like this. Trace your right hand, you'd get something like this. And you can see they're mirror images of each other, right? If you just mirrored this right hand one, you get a left hand one. And if you've ever looked closely at how your iPhone takes selfies and held up your right hand in one of those selfies, I swear to tell the truth, the whole truth, nothing but the truth. The iPhone is actually going to flip that for reasons I've never fully understood. But Also, if you just look in the bathroom mirror and you hold up a right hand, it actually looks like your mirror twin is holding up a left hand. So left and right hand are converted into each other by a mirroring. So we would say that there's a parity transformation between these two hands. But we have a little problem, which is that a 2D tracing can be rotated using 3D into its mirror image. So I can just imagine that I take this black tracing, and I just pull it out of the page, flip it, and rotate it to overlap with this guy. And this is a problem because, as I said, in cosmology, we invoke isotropy. We invoke the idea that the laws of physics are the same every direction you look, the same under rotations. So the problem is, if I apply that rotation symmetry to this setup, I'm not going to be able to tell the difference. I can't probe parity with the 2D observable because under rotations, there is no difference in parity preserved. So a very kind of macabre example of this is if you got bored during my talk and decided I really don't like this guy, I'm going to cut off his right hand and cut off his left hand. And if you then put my right hand and left hand into a bag and shook the bag, that would rotate the hands. But if someone else said, that's not very nice, I think that's against the code of conduct to be cutting off speakers' hands, let's put them back on, that person could pull them out of the bag, and even after you'd shaken the bag, they could reattach them to the correct arms because a right hand is still a right hand, no matter how you rotate it, because it's 3D, right? So we can actually tell our left from our right, and it's because it's a 3D hand, right? It's not just a tracing. We've also got the palm and the top of the hand and the thumb coming out. And you can tie this to my X, Y, Z comment about coordinate systems, because you can think of, let's imagine, that your palm is giving you one vector, the top of your hand's giving you another vector, and your thumb's giving you a third vector. So a 3D object like a hand, if there's some breaking of the symmetry, which there is because palm is different from the top, 3D object like a hand gives you a 3D coordinate system. So we need 3D to probe parity. If you take nothing else from the talk, take that away. That sounds dead simple, but of course it has a science tie-on. Roman is spectroscopic. We have 3D information on the galaxy positions. So we need a spectroscopic survey like Roman, or a very good photometric one, to get 3D galaxy positions to probe parity. Okay, so as I said, we need a 3D statistic. So I'll just step you through why some of the standard workhorses in cosmology won't do the trick. So in cosmology, we love to measure 2-point correlation functions. This is just the excess of pairs of galaxies over what a spatially random distribution would have. So let's imagine that you just put one hand on a galaxy, and then you make a line of fixed length, and you rotate that around and ask, how many galaxies do I see around this first one, but keeping the length of the line fixed? And then you do that for different lengths of the line and make a histogram. This is just a 2-point correlation function. And the geometry, as I said, is a line. But the problem is a line is one-dimensional. A line looks the same in the mirror. So a line definitely won't work for parity because, as I said, we need 3D for parity. So we could try the next thing, a 3-point function. But a 3-point function is a triangle. It's just asking how many triples of galaxies do you have above random. But as we all know, a triangle lies in a plane. It's 2D, so we're going to be back to this problem that we had with the hand tracings a few slides ago, that they can be rotated into the mirror images. So a 3-point correlation function, which describes triangles, also won't let you probe parity because it's just a 2D statistic. So then if we ask, what about a 4-point correlation function? Then the answer is yes, we can probe parity because 4 points are going to be a triangle and 1 point above or below them. So it's a 3D figure. And so the galaxy 4-point correlation function is the lowest order 3D statistic, and it probes an excess of tetrahedra over a spatially random distribution. And it's already by construction rotation and translation invariant corresponding to isotropy, and then homogeneity is why we have translation invariance. We think the laws of physics are the same over here as they are over there, same in Pasadena as in LA or as in Berkeley. And so this idea of searching for parity with the 4-point function was proposed by myself and Bob, Khan, and Jamin in our PRL in 2022. And in the rest of the talk, I'm just going to show you intriguing first results from the BOSS Galaxy survey, where we actually seem to be seeing a signal of parity violation. and then I'll connect with how Roman can really follow this up. So one slide with some scary math and then no more, I promise. We need a way to parameterize the 4-point correlation function. What we do is we split it into these isotropic basis functions that depend on the 3 unit vectors, the 3 angles from the top of this tetrahedron. So sit at this red point, R1 hat, R2 hat, and R3 hat are these 3 vectors pointing out. And you can just form a set of rotation invariant functions of them. This is the formula for them. It's just 3 spherical harmonics weighted by a 3J symbol. That's a Clebsch-Gordon coefficient up to sine and rescaling, if you prefer that. And these are just basis functions. So if we expand the 4-point function in them, all the physics is in this red box. This radial coefficient will capture how many tetrahedra do you have as a function of side length. And at each L, where you've traded these angular degrees of freedom here, the directions, for a discrete set of indices, L1, L2, L3. And so you can not worry too much about the math of this if you like. There's a very long paper by me and Bob on the properties of these. And also I figured out a generating function for these in recent work. But the key is all physics is now in the red coefficient. So we just have to measure this. And an intriguing property of this basis is it actually splits into even and odd modes. So the odd modes will actually capture an imbalance of tetrahedra and their mirror images. So here I've just put a tetrahedron and its mirror image. We rank the sides so that you have a unique sense of which is the first, second, and third. We just order by length. And it will turn out that the odd modes of our basis are all proportional to the signed volume of the tetrahedron. If you do a spatial inversion, you're turning the tetrahedron inside out, so you're going to flip the sign of the signed volume. So then if you add them up, if you get some net overall volume that's different from 0, it means you had more of the inside out than the outside out guys. You had a parity violation. And so just one quick slide on the computational side. We put this together into a code that we accelerated with GPUs. Projecting onto this basis that we've designed is a very high arithmetic intensity problem, lots of floating point operations per second. So we designed this code called cadenza, which actually does 2 through 6 point correlation functions. This is the first time that the 5 and 6 point have ever been accessible in cosmology. So that's kind of unexplored territory. But the bottom line is this GPUization gives you 140x speed up over a CPU, and it lets us do these calculations for all the boss galaxies in about a half an hour on one NVIDIA A100 core, which I've hidden in here. So this was led by my postdoc, Jia Min. She labored heroically to get all the minus signs right, but also many other folks listed here contributed. So with the code in hand, we can do a measurement. This is what it looks like. And this is just showing you different angular basis function modes on the boss data. Notice all these L's add up to odd numbers. 1 + 1 + 1 is 3. 1 + 2 + 2 is 5. That's because these are all the odd parity modes. That's what we want, parity violation. And what we've done is we've taken the dependence on the 3 side lengths of the tetrahedron. Remember, it's shown here. So it depends on R1, R2, and R3. And we've mapped that to a 1D radial bin index, so you can plot it. And then we're splitting these panels by the angular mode, which is describing, if you sit at this red point, what's the kind of angle dependence. And so I just show this to give you a feel for the data. By the way, red is the north part of the boss survey. Blue is the southern part. It's split by the Milky Way, which you can't see through. I just give you this to show you it looks like noise. Basically, this is not something where you just see the signal and, like that famous possible SETI signal, you can just say, wow, there's a bump. This really looks like noise. So the power of this analysis comes from taking 23 panels like this. Each has hundreds or more degrees of freedom. And we add them up. We weight them by the inverse error bars. And then you get some overall chi-squared. And that's our kind of test statistic. So that's what I'll show you here. This is, I've simplified the language, but chi-squared is on the x-axis. This is your total parity violated signal co-added up over, co-added up over many, many panels that each look like this. And what we've done here is These are mock catalogs that have no parity violation. So these are realistic mocks for the BOSS survey. They've got galaxy physics, gravity, some matching of the clustering by how we put, galaxies into halos. They have observational systematics. They're a kind of null case. This would be what the universe looks like if we've understood all the physics. And this is actually a histogram of 2,000 of them. But then this is our data in this orange line. So what we did is very simple. We just said, okay, this is our kind of no parity violating signal. There's some scatter about it. What's the width of that scatter? And how far away from that is the data in those units? So we see that our data is actually 7 sigma away from the mean of the mocks as regards the total parity violating signal. And I want to emphasize this is model independent. In the standard model, you should have 0 parity violation. So anything non-zero in a statistically significant way, as we seem to see here, is exciting, possibly new physics if we've gotten all the systematics controlled. So in the last 3 or so minutes, I'll try to tell you what comes next. So one thing that comes next is DESI, dark energy spectroscopic instrument. That's in this nice tower here, and it's from the ground. We've got about 7 million redshifts in year 1 through 3. Sorry for bringing this up. We've got quite a few redshifts on disk already, so Jiamin and I and Bob are carrying out a DESI analysis. But of course, the star of the show today, which needs no introduction, is Roman. So I want to tell you a little bit about why Roman will be exciting for this problem. So these are some forecasts. I quickly adapted a figure we made for DESI, but I'll focus on the golden Roman line. What we did here is simple. We said, let's suppose the BOSS signal that I showed you is real at roughly 5 sigma. Let's then just scale it up to what DESI will do, scale it up to what Roman will do. So here, I've kind of tried to guess where Roman would lie on this. Roman has such high number density that basically won't contribute to the errors on the scales we're using. And so in that limit, the things like galaxy bias and redshift space distortions and growth factor actually cancel out of the signal to noise. So Roman is in a very interesting regime for forecasting. My guess is that it won't do quite as well as DESI because it's basically 1/7 the area on the sky of DESI, and volume really helps you in this game. It turns out these forecasts scale as volume, not square root of volume. So that's why Roman's a little bit worse than the DESI luminous red galaxy sample, but there's some tricks here. This is DESI year 5, so we won't have that until like 2027, 2028 anyways. By that time, we'll already start to see the Roman data. So it's not like Roman is going to have to follow after this result being so high. But perhaps more importantly, Roman will have a totally different method from ground-based fiber-fed spectrographs. So BOSS was ground-based fiber-fed. DESI is exactly the same technology, but with robotic fiber positioners. A lot of the software is shared. A lot of the team is shared. The ideas behind how this is done are all the same. That means that if there's some weird unknown in BOSS, it could propagate to DESI too. I hope very much that it won't, but you just have enough shared aspects of the design and people and code in these two surveys that what I'd really like to see is a totally different instrument with a totally different technology doing this instead. So Roman, by virtue of being in space, in the infrared, with a GRISM, different team of people, will just be a really, I think, compelling thing. And to go back to this forecast, Roman should, I think, be able to see this effect at more than 10 sigma if it's real. So admittedly, DESI could see it at maybe 20, 30, or 40. But at the point where you have 10 sigma or more on new physics, who cares? You don't care about 10 sigma versus 15. What you really care is, did I get it right? Is this real at all? And in that context, you'd much rather have 2 different surveys that are both confirming it at quite high significance with very different methods. So I think that's the real importance of Roman. Another aspect of Roman that will really, I think, be transformative here is it has a different higher redshift galaxy population by virtue of being space-based and infrared. So this is good for 2 reasons. One is it adds confidence the signal is not some weird population effect in the BOSS and DESI galaxy populations. Maybe there's some funky evolution, something we don't understand about luminous red galaxies. Well, Roman will be a different galaxy population, higher redshift universe, totally different physics going on at these redshift of order 2 times. Secondly, being at higher redshift means you have less nonlinear structure formation under gravity. And that means that our error bars, our covariance matrix, is much better controlled. Because one thing I hid from you due to time is we have an analytic formula to compute our error bars that's valid in the Gaussian random field. So it basically assumes the universe is as it was at the beginning, no gravitational evolution. That assumption is much better at higher redshift. Good. So just one quick taste of what could it all mean. There are actually models out there that propose parity violation during inflation. As I said, the most vanilla standard model plus inflation doesn't do this. One example of what does do this is axions, where basically you have this FF dual coupling. So this is kind of like a dark sector electromagnetism. And it turns out to be able to generate a parity violating set of fluctuations in the initial curvature, which then seeds the distribution of galaxies. And it's really because this quantity E field dot a B field is parity odd. So it's a parity odd driving term driving these fluctuations delta phi in the inflaton field. And we think the inflaton field is what produces matter. So this is just one example of many, many models people have explored and are exploring. And my grad student, Matthew, is working this model out. So this is really just to give you a flavor that there is not just one, but in fact, many different theory interpretations that would meet with this if the signal we're finding is real. So with that, I'll give you the summary. I've hopefully given you an intuition as to why the galaxy 4-point function can probe parity violation and why we need it, why 2 and 3 won't work. We have a fast algorithm to do it. We've measured on the largest currently extant sample, roughly 1 million galaxies in BOSS. We found pretty statistically significant evidence for it, but we'd like to see if that's real. And what we need to do is confirm it with other samples such as Roman to see if it's real. So thank you very much.
Okay, so we have time for a couple of questions for Zach. Yes.
Thank you. Are there systematics that you would worry about in terms of redshift accuracy at the scale of, let's say, 1 footprint? And if so, how good would you need your redshifts to be? What's the wavelength calibration requirement?
Great, thank you. I missed one word you said, redshift accuracy at the scale of what?
Like a footprint on the sky, so half a degree.
Right, so you're saying if I had some variations in redshift accuracy across the footprint of the survey or the footprint of just one Roman observation?
Just one pointing. So how well do you have to get the wavelength accuracy calibrated over the full field of view?
Great, that's a great question. So I think as long as the redshift errors are random, that wouldn't be a problem because we're basically binning our analysis where we say, look, we're gonna take these tetrahedra and slice the sides into chunks of order 10 megaparsecs. So as long as your random redshift errors aren't blurring things a lot more than 10 megaparsecs, that should be okay. Now, if there's some systematic trend in the redshift accuracy where I have my, field of view, but I have worse redshift errors on the left than on the right, even if it's just worse errors but random, so let's say I have, a 15% error on the left, but a 10% error on the right, I don't think that would do it. What could do it is if you actually have some modulation of the number of galaxies that's left, right? So an interesting effect we found in BOSS was that the cameras were less efficient on one side of the plate than on the other by just a tiny bit. And that was giving you a left-right asymmetry. And then it was also tending to lose fainter galaxies. Fainter galaxies are typically farther away. So that was giving you a Z asymmetry. So now you had an X, Y, and Z asymmetry. That's 3D. So that could be parity odd. And we actually looked into that with BOSS by just empirically doubling the pattern. We said, let's throw out double the number of galaxies based on their fiber magnitude and see, does that move our result? And it does affect it. It moved us by about 2 sigma, but moving 7 by 2 doesn't make it, consistent with 0. So I think we could play similar games with Roman, where if we see, okay, there's some kind of weird asymmetric redshift error, let's just make it 2 times worse and kind of compute the derivative and find out. But yeah, I think subtle effects like that are really, that falls into the unknown unknowns, which is why I think Roman will be so good, because it's just going to have different ones than Boston Desi.
We have time for one more.
Okay, just at the risk of annoying the entire audience, are you thinking about Euclid?
Good. Are we thinking about Euclid? I wasn't going to mention that word today.
But yeah, it's you should, right? We should think about landscape's going to be in how Rome.
Yeah, I think we would love to do this analysis with Euclid as well. And that data set will be maybe a little sooner than Roman, but we aren't, my team isn't as embedded with Euclid in terms of having the kind of ground level. Yeah, that's true.
If it's just volume or size, probably do lot its accuracy. And there are other things where Roman, because of the calibration, really solves some of the issues that we just.
Yeah, that's a good point. Maybe we can. Yeah, good. Let's talk more over coffee. I think that would be great to think about the trade-offs there.
Well, let's thank Zach again.